good morning, everyone. My goal here today is really to help you be more knowledgeable and raise your awareness of how you can improve the safety and the reliability of your electrical power system, because those two things do go hand in hand. And that's where sometimes you guys might have heard the phrase, the art and science of protective devices, because we can make a system very reliable or we can make a system very safe. And what we're usually trying to achieve is a balance. And we've got a lot of standards out there that we're all trying to adhere to. And just a moment about the IEEE 1584. It is the guide for performing arc flash hazard calculations, and it was recently, and I say recently, updated, but the 2018 version is now basically becoming into effect. And really, there's a number of changes that I'll mention in here to talk about, changes to arc flash boundary calculations and some other issues or challenges that have been in the 70, or not the 70, but the 1584. And once again, just making sure that your study is still valid, because once again, a valid study is critical to, once again, improving the safety of your power system and those that have to work on it and around it. Just a brief summary of those changes. There's been a recent revision to the voltage classifications and definitions, aligning those, low voltage, medium voltage, high voltage with other standards. There's changes to bolted fault current levels, an updated electrode configuration. And what that basically means is if it's horizontal bus or vertical bus, that has different arc flash values based on those orientations. And so the new software incorporates that type of data into the calculation. Enclosure size, this is actually a big one for a lot of folks. If it's an open air explosion, it kind of goes 360 degrees. If it's a big box, it's not quite as focused. But as the boxes get smaller and shallower, the enclosure size really can turn what might be a more minor fault in a much more focused fault, and at least focused on the individual standing in front of it. They're going to remove the ground system, or the system grounding variable, and then inclusion of minimum distances. And then one of the biggest takeaways, I think, from some of those changes is there are changes, right? There's changes in the standard, there's changes in your system, and it's important that you revisit these studies every 5 years. Now, that's not to be confused with you have to redo your study every 5 years, but you do need to take into account that there have been these changes, and you might have situations where your arc flash could be reduced, and those new labels would actually allow the people working on that equipment to wear the appropriate PPE, because that's always about appropriate. We don't want to wear more PPE than we need. We want to wear the appropriate PPE. But because of these changes as well, especially on the enclosure size, we might find that there are actually situations where the arc flash is higher, and now somebody might be underprotected. And of course, that would be the worst case scenario, is individuals being underprotected. Overprotection, it's uncomfortable. Underprotection is could be catastrophic and hazardous to people. So the other thing we're going to talk about, and I'm going to weave in here, as Justin mentioned, is we're going to dive into breaker maintenance, breaker testing, protective devices, because in the NFPA 70E, Article 205, the general maintenance requirements, there's a couple of different things we need to look at. One of them is 205.3, the general maintenance requirement, where electrical equipment, your breakers, your transformers, your switches, shall be maintained in accordance with manufacturer's instructions and other consensus standards like the NETA acceptance and maintenance testing standards, as well as 205.4, specifically talking about overcurrent protective devices and how those devices need to be maintained. And in a nutshell, and I'll probably say this again as I go through this presentation, if your overcurrent devices are not operating properly, not set to your coordination and arc flash study, then the arc flash hazard that the individual will be subjected to could be much higher than the study and the label on the equipment would otherwise say. So it's important that we periodically check our equipment to make sure it's operating properly. And I'm also going to talk a little bit about the fact that, we want to do, I like to look at the power system in a life cycle, right? When it's brand new, we want to do acceptance testing. We want to make sure that, once again, is the coordination study implemented? Is the arc flash study implemented into our settings? Is the equipment going to operate properly right out of the box, if you will? Then the next portion of the life cycle is maintenance, right? And I don't know exactly who's on the call with us today, but you could be at a different point in the life cycle, right? You could be at the acceptance testing, you could be at the maintenance testing, you could be at the end of life, right? And so once again, maintenance testing is an important cycle, and this is really where we speak to that continual ongoing maintenance of the equipment. And then finally, whether it's a system modernization of a system that's relatively new and taking advantage of new technology, or you've got an aging system and you need to modernize it and upgrade trip units, upgrade breakers, and those sorts of opportunities. So once again, we're going to kind of walk through that whole life cycle of your system and give you ideas where you can continue to modernize and once again, improve the safety and the reliability of your power system. So this next slide, we want to start with acceptance testing. And as Plato is quoted as saying, the beginning is the most important part. If we start our system off properly, then we can have more confidence that it's going to deliver those two things, safety and reliability. And, once again, it starts off with things like component testing. And, you guys can see part of our team here doing primary injection testing of some low voltage circuit breakers in here in the background. And, this is important. This is part of that, ensuring those protective devices are working and to test that the settings are set properly. And then, of course, once again, so it's about component testing in a lot of cases. And here's a couple of common problems that we see in the field when we're doing acceptance testing. And these are things that I think are, crucial for you to be aware of, to ask questions of the folks that are doing your acceptance testing. And it doesn't matter to me whether it's the manufacturer doing the acceptance testing or a third-party NETA company like ours doing the acceptance testing. There are critical points to look at. And one of them is, this is a picture of a breaker I took recently where it had been in service for probably more than a year. And they were having some nuisance trips. Once again, they weren't having arc flash issues, but they were having nuisance trips. And so we got called in to investigate that. And what we found, and I can point it out here with my pointer, hopefully everybody can see this, this ground fault setting is set to A, and without going into a lot of detail, A is the minimum setting. And on this particular breaker, that is probably only a few hundred amps of imbalance. And once again, was causing that nuisance tripping. Also very short time delay. And we can also point out that there were other things set at minimum. There's short time set at minimum, instantaneous set at minimum. So from a reliability standpoint, this breaker was not set per a coordination study. I can tell you that just by looking at it. I don't even have to see the study to know that. Because once again, the short time, instantaneous, and ground fault in theory don't coordinate with breakers downstream, once again, leading to their problem. So it's important that somebody check this. And once again, whether this was a manufacturer startup that it didn't get implemented, whether there was a third party involved, I don't know. But what I do know is that we got to make sure that these things get checked. Because if we don't, then we run into a problem. The other thing to talk about is, we work in conjunction sometimes with manufacturers, right? And manufacturer tested gear from the factory, and I'm manufacturer agnostic. Everybody has these things called human beings that work in their plant and that put these systems together. And admittedly, we are all fallible. We all make mistakes. And part of our job is to help identify those mistakes before in acceptance testing, before the system goes into service. And, we as a NETA third-party testing company would do different tests in many cases than the manufacturer does. And so because we do different tests, sometimes we find problems that the factory doesn't find. And here's a great example. We were doing ground fault testing of circuit breakers, similar to the ones I showed you in the previous slide. And we do primary current testing. So we inject current through the breaker to make sure it trips on the ground fault, and then we inject current through the breaker and through the neutral CT to make sure that it doesn't trip. So once again, prove the ground fault works, safety, prove the ground fault doesn't trip when it's not supposed to, reliability. And what we found is that system was not working properly. It was tripping both when we injected it and expected it to trip, and when we injected it and didn't expect it to trip. And some investigation found that, you'll notice right here, we've got a red and black wire, both landed in slot T1, nothing in T2. A quick review of the drawings, and we said, okay, well, we can see from the drawings that the black wire is supposed to be in T2, red wire in T1. Made that change, retested it. Now the system's working properly again. And once again, important test in this particular case about reliability. But once again, there are other issues that can come into play when we look at this from an arc flash standpoint, because once again, if the settings aren't proper, if the devices aren't working properly to start with, then once again, it can lead to problems down the road. And our job is to head those off and provide a system to you that is complete and working properly. So some other things to talk about is that, this is a great example of what an acceptance testing project might look like. Pieces and parts laying everywhere, plastic covering equipment, and medium voltage gear and cable, low voltage gear. And once again, manufacturers in a lot of cases will come in, they will test their components, but do they always test all of the equipment that connects these devices? And in a lot of cases, manufacturer testing would not include things like cable testing. Oops, wrong slide, wrong button. Wouldn't include things like cable testing. And so once again, this is another offering that we do to make sure that the system's going to operate properly, because once again, an untested cable, you don't know its condition. Untested transformers, you may not know their condition. And then I should also mention, just because there's dirt in this picture, that the grounding system, once again, that's another area where a third-party independent testing company might be of service to you, even if you're getting manufacturer testing, because in a lot of cases, the manufacturer's testing their gear, not necessarily all of the system. And part of what we want to have, of course, for arc flash safety is a properly grounded system. And of course, that starts with the rods and copper that they put in the dirt to make sure that there is an earth connection. So we would do things like a fall of potential test on a grounding triad or a grounding mat, and then point-to-point checks. Is that stinger coming up to your transformer? Is that ground lead coming up to your low voltage switch gear connected to the ground grid? So once again, simple checks in a lot of cases, but vital to ensure that your system starts off with a best possible case for operating tirelessly and reliably and safely for decades to come. Turning our attention now to maintenance testing, and I like to point out, as Aristotle says, quality is not an accident, it is a habit, right? Quality is not an accident, it's a habit. And the habit of doing regular maintenance testing is critical to your system reliability and to your system safety. And I love this slide, and some of this may be lost on some of you depending on how intimate you are with how particularly medium voltage power systems are put together and are expected to work. But this is an 86 device, and this 86 device, as you can probably recognize, has gotten really, really hot, and it's basically broken now. It's not going to work. And this problem was created because of operator error, right? An operator didn't understand how to reset an 86, and in the process of trying to do what he thought was the best thing for getting his plant back online, basically destroyed this 86 device. So it can't do its job anymore. And its job is to take a trip input from a protective relay and then send that out to the rest of the system to trip multiple breakers and lock them out so that they cannot be reclosed into a fault. Well, because this 86 device is defective now, the relay can say trip all it wants. Trip, please trip. We're going to burn this thing to the ground if we don't trip. And that 86 is just going to sit there closed and allow that fault to continue. And this particular 86 caused a catastrophic, or was, I shouldn't say caused it, it was the weak link in the chain, and caused a piece of 15 kV switchgear to basically literally burn to the ground until the utility finally was able, utility relays were finally able to clear it. And so once again, each one of these components is super critical to be checked. Do we check 86s every year? In some cases, yes, in some cases, no. But once again, we got to periodically develop that habit of looking for problems and finding problems and fixing them, right? Not just addressing the symptoms, but fixing them. And, once again, so what does maintenance testing look like? In some cases, it's just a matter of like good housekeeping and walking around. And, I wish I could hear some of you guys online saying, what the heck is going on right here? So what we have here is a customer that was having some nuisance breaker tripping. These fairly large frame air breakers were tripping. And of course, that causes production problems in the plant. And so their solution to keep those breakers from tripping was not good maintenance. It wasn't checking my coordination study. It wasn't finding where the problems were. It was, let's jam a 4x4 into the frame of the breaker so that the breaker can't trip. Now, as all of you can imagine, that, oh, I can't believe somebody would possibly do that. But as I like to say, I'm from the Navy, this ain't no bullshit. This really fast. We didn't stage this picture. We took this picture when we were doing a job walk. And so once again, backing up, if this breaker can't trip, then any arc flash study that's been conducted of the devices downstream is completely invalid. There is no way that the breaker can trip, which means if there were to be a fault downstream, it's going to be much more catastrophic than the arc flash labeling, the arc flash study would predict. So once again, I know this is a graphic error, illustration of a problem, but it does happen. The other thing we find oftentimes too when we're doing maintenance is just things that, just any, I like to say any electrical mechanical piece of equipment can fail at any time for no apparent reason. And, here's a great example of a residual neutral CT that's part of the ground fault system for this breaker. And it's an ITE CT, and ITE is notorious for having what they call the ITE melt. And essentially what happens is the casing of the CT just melts away, and it's not related to heat. It's actually strangely related to humidity and the age of the equipment, because this is aged equipment to be sure. But when we open up a door during maintenance and we find something like this was a hidden failure waiting to basically injure somebody or shut your plant down unexpectedly. Because if you don't ever open these covers and do regular maintenance, you wouldn't know that a problem like that exists. So once again, an easy way for me to illustrate the importance of doing regular maintenance, because we find problems like this almost every day. Let's talk a little bit about some other things that, once again, routine maintenance can find. And, today's topic is not about talking about partial discharge or anything like that. But once again, when we open up equipment, and like this is a transformer, we're going to do some transformer testing on it. And we find little things like this. This is basically a 15 kV piece of jumper cable, the red cable, laying adjacent to a hard piece of bus that's interconnecting parts of the transformer. And you'll notice that white spot on both the bar and the cable. That's corona happening. That's partial discharge occurring between those two conductors at different voltage planes. And once again, left unchecked, this is going to become an arc flash. Now, is it going to injure people? I don't know. But is it going to shut your plant down? Highly likely, right? And so once again, these are the kind of things that we're looking for, and we find, like I say, routinely when we're doing system maintenance. I like to point out this one too. I don't know how many folks on the call have medium voltage air switches, but this is a great time of year to talk about medium voltage air switches, because what you'll see what look like little cigarette burns or rust spots here on the back of the wall might look innocuous, right? Like no big deal. But what those indicate to the trained observer, like myself, is there's partial discharge occurring, right? Little small tracking events from the primary conductor here to a grounded plane. And when those occur in the situation I'm showing here, no big deal. It's burning the back of the board a little bit, but left unchecked, this becomes an arc flash event, because once again, most of our arc flash events start off phase to ground. And this is a perfect example of the precursor to a failure being caught before it fails. Now, I mentioned this is a great time of year to talk about this problem, because what precipitates this, what drives this in a lot of cases, this particular example, is moisture, right? I don't know about where everybody's at from around the country, but right now, sometimes we have really kind of cool, damp mornings, and then the dry morning, then the sun comes up and everything warms up and we get some condensation going. And of course, there's supposed to be operating heaters in these types of cabinets to minimize condensation, minimize that moisture. But in a lot of cases, heaters aren't hooked up. Once again, that goes back to good acceptance testing. Are those heaters hooked up properly and working properly when it was acceptance tested? And then good maintenance testing. Heaters fail, your fuses blow. And once again, those heaters, if they're not working, can lead to partial discharge, and like I say, ultimately lead to some arc flash hazards that would be unexpected in a normal maintenance, in a normal operating situation. So a couple of things to keep in mind when we talk about maintenance testing. Another one that we talk about is just aging trip units and moisture. And I'm going to mention moisture again here on this this particular slide talk. Once again, aging trip units more than likely are going to cause you nuisance tripping, right? Sometimes they just don't operate at all. And that's, once again, why we periodically need to test our trip units. We periodically need to inject them either with secondary current or primary current so that we can continue to make sure they operate. And once again, and I've had a number of these, and I'll mention it really briefly, is we've had a lot of nuisance trips lately. People are like, why is my breaker tripping? And then it trips faster and it trips fast. That's usually an indication that there's an electronics problem. And most people don't like to hear this. What's the solution to an electronics problem when a breaker's tripping? Take that trip unit out or take that breaker out and replace it with another one. I apologize. I hate that, but there's no real easy fix for a breaker that's nuisance tripping in that fashion. And I'm happy to take that offline with anybody that's curious. And then the other picture in this slide, and I just love this story. We had a customer, once again, breaker was nuisance tripping, and we saw one little water spot. You know that when you get like a drop or two of water and it leaves that little white residue, like on your coffee table? Well, this breaker had one little drop of water, what looked like one little drop of water that hit the top of it, but it was actually a little bit more than that. And it actually got into the electronics of the trip unit and caused a failure. So if you ever have an event where, for whatever reason, you get a significant amount of moisture in the room, maybe a pipe's leaking, you really need to take that seriously and look hard at those breakers, because if nothing else, from a reliability standpoint, they're probably going to be in jeopardy. And obviously, anytime something's not operating properly, it can lead to a safety issue and once again, invalidate your arc flash study that you've conducted. I kind of talked a little bit about negligence, a little bit about, hey, how do I know my system's operating reliably if I don't do maintenance? And once again, these are graphic examples of of neglect. And once again, for those of you on the call that might have medium voltage systems, just about every medium voltage system has some kind of DC battery system that is there to both power the trip units if they're microprocessor or solid state, and provide the power to trip breakers when they're called to trip and close them, but we're talking mostly about the safety. And so once again, if this battery system, and you can obviously see, if anybody's ever popped the hood on your car and you see a battery system like this in your car, you kind of know why your car's not starting, right? So same thing here. Once again, a graphic example of a battery system that's been really neglected. But if this battery system is not working properly, then all of the breakers that are relying on it, all the protective devices that are relying on that to trip, ain't going to happen. And once again, when the breakers can't trip, your arc flash study is out the window. It's invalid. And then, like I say, just routine maintenance. I mean, once again, you can see the sawdust in this picture. Will this Pringle switch open? Maybe it will, maybe it won't, right? It's kind of a 50-50 shot. And even if it does open, we've got combustible material all piled up in this breaker. So could this catch fire? Sure. If there were to be an arc flash event, could it be even more catastrophic? Because once again, an arc flash event, relatively short in the big scheme of things, but what really is going to do the damage after the arc flash event is all of that combustible material. It's the same problem we have when, once again, when we talk about, individuals being exposed to an arc flash. The arc flash is really usually relatively short. It's the continual burning of any kind of flammable clothing that actually injures people more than the arc flash, right? So once again, we got to make sure that our equipment is not in this kind of condition, because if it is, once again, your reliability is probably 50-50. And of course, yeah.
You work in field services, so I was just curious. I mean, how often are you coming across situations like this? Because, you said earlier, Aristotle says equality is a habit, and he definitely would not approve of what we're seeing here. It's neglect, right?
Yeah, and you would be, I guess I'm continually surprised, right? Once again, I'll answer the question like this. Most of our clients are about routine maintenance, right? And so if we're doing that routine maintenance, or if they're doing it with somebody else, typically you don't find things like this. However, I walk into plants on a regular basis that say, gosh, I haven't done maintenance in 10, 12 years. And I don't have a slide for this, Justin, but it was an IEEE. I'm gonna draw a blank on the one, but they did a study about the time frame between testing a component and its probability of failure, right? And the basic numbers bore out that if you don't inspect and test your equipment at 3 to 5 years is sort of the interval that they've come up with, 3 to 5 years, that the probability of, say, a circuit breaker not operating properly is relatively 50-50, right? That it's 50% chance it will, 50% chance it won't operate properly if it's gone more than 3 to 5 years. So I guess we should stress to everybody that if you are doing routine maintenance every 3 to 5 years, you probably have got a pretty good system going. If you haven't done maintenance in 10, 12, I got a customer right now that maybe hasn't done maintenance in 20 years. I'm expecting we're going to find problems, right? And it's a matter of how we address those then at that point. Good question. Good question. And I've mentioned it before. We're about solving problems, not fixing symptoms. And once again, everybody can see this is a medium voltage vacuum breaker, discolored pole here, nice shiny pole there. And a company had condemned this entire breaker, saying that it needed to be replaced, and that's an expensive component, as you might imagine. And we got asked to give them a second opinion. And our technicians did a little bit more diagnostic type testing and actually found that it was not an entire bad vacuum bottle and pole assembly, but this flexible strap that's connected to the bottom of the vacuum bottle. And so we were able to fix this for a few $1,000s as opposed to tens of thousands of dollars. So once again, we got, and I mentioned the breakers that are nuisance tripping. That's a symptom, right? It's a symptom of the problem. It's not the problem. The problem is actually the electronics of the trip unit, right? So make sure that you're utilizing companies and practices and procedures that are going to solve the problem, not just put a Band-Aid on the symptom. So let's move into some talk about system modernization, right? And this is an opportunity both for new systems and older systems to take advantage of all the new technology that's out there. And in the picture here, we got an RL breaker by Siemens, really reliable airframe breaker. These can be remanufactured over and over again. Check in with myself if you have any kind of needs like that. But in particular, I want to point out here in the bottom right corner, this breaker, which probably was originally built with a static trip 2 trip unit, I'm going to say a solid state trip unit, really good in the day, but those are notoriously failing on a more regular basis. And so once again, we take the opportunity to upgrade that. And in this picture here is an AC Pro 2. And what's special about an AC Pro 2? What's special about taking advantage of some of these modern trip units is, one, from an arc flash standpoint, they're more selectable, right? I can have down to a few amps. We can adjust that current and make both better coordination and lower arc flash let through because of the settings that we can put into these trip units. The other nice feature about the AC Pro 2 over the AC Pro 1 over any other retrofit trip unit that I'm aware of is they have what's called the sluggish breaker feature. And so essentially when the breaker is brand new, right, we put this trip unit on it and we test this breaker on the high current test set. We know that if the trip unit sends a signal to trip the breaker is going to take, let's just say 33 milliseconds to respond and open. And so we can program this trip unit to say, hey, this breaker should trip in 33 milliseconds. If the next time this breaker trips and it takes 50 milliseconds, it's still pretty fast, but it's not as fast as we program the trip unit. And then what we might find is that the breaker needs some additional maintenance, right? Because once again, our coordination study, our arc flash studies are based on these breakers operating by design, right? And so if all of a sudden we have a breaker that's operating just a little slower, then that's going to make our arc flash hazard just a little higher, right? Just a little higher. So once again, the sluggish breaker feature that is now in some of these trip units is spectacular for, once again, knowing without even doing maintenance, hey, is this breaker operating properly?
Mose, got a question for you real fast. Our first one of the day, which is great. So this question says, you mentioned 3 to 5 years testing period. Is this specified in a standard somewhere? And at some plants, it is hard to get access to certain breakers, even on a shutdown. I have found operations usually pushing back on certain breakers, requiring a lot of switching.
Yeah, it is always there. There are always customers and situations and systems where, yes, it is a challenge to take an outage on a particular device. And in some cases, I like to use the phrase that any activity is better than inactivity. So, just using the breaker picture, if you say, hey, Mose, I can't shut this circuit down for you to do a complete test on this breaker. Okay, well, can I just simulate a fault to the trip unit, trip it, and then close the breaker back? Yeah, I can take a 5-minute outage. Okay, just opening that breaker and closing that breaker is great maintenance, right? Just cycling these devices, because once again, if they sit there closed for years and years and years, and you expect that mechanism to work properly and all the rollers and the lubrication, and that's a whole nother presentation, really. But once again, just opening and closing them, that's maintenance, even if you can't take a longer window, or maybe you don't have time to primary inject this breaker, but you got time to secondary inject it. So what activity can you implement? And then as far going back to the question about, hey, where is it written 3 to 5 years? Most of your manufacturers do have some references in their literature that there is a routine maintenance cycle they recommend, and it typically falls in that 3 to 5 year window. NETA has a matrix, and that matrix basically takes into account the criticality of the equipment, the age of the equipment, and the condition, right? So if you've got a data center and you've got controlled spaces and your equipment's relatively new, you might be able to extend that maintenance cycle out more towards the 5-year portion. If you've got a sawmill and the gears in a shed, and it's really critical because if that goes down, the plant's going to be down. Or, and once again, if you got kind of a cruddy system, maybe the arc flash is more concerned, then you might want to move that periodicity up to every year, right? And it all depends on kind of those multiple factors. Can I afford to do it? Do I have the time and the commitment from my production side of the organization to do it? And then what's the worst case if I don't do it, right? And if the worst case is, I just turn it back on, or I fix it when it fails. And then there's a lot of people that run to failure, right? Run to failure is an option. And I don't have the slide for it. An NFPA 70B is probably the best example and probably has some of the best references for this periodicity. But in the NFPA 70B, there is a chart, and basically it's a graph where they say the cost of maintenance, the cost of replacement, and those two lines at some point intersect, right? If I could spend a ton of money on maintenance and minimize my failures, or I can spend no money on maintenance and my cost to repair and replace will go up. And there's a point where those two intersect. And that's maybe more of a financial decision. But, once again, those things are all kind of driven together. And once again, plenty of references out there. And if somebody wants, we can certainly provide the NETA matrix. You can get the 70B from the NFPA website. And there's plenty of articles out there as well. And I wish I had the other IEEE standard that I referenced that basically talks about those 3 to 5 years, whether a breaker will work or not. But we can share that with anybody that's interested, and then Justin, they can email you, and then you and I can get that information to them.
Yeah, thanks, Mose. Jason says here it's important to note that NFPA 70B is set to become a standard next year. Currently is only recommended practice.
That is correct.
And one more here. Are the AC Pro 2 network able into PI or some other metering system?
I'm not a communications guru or intimate with that, but the basic answer is yes. The AC Pro 2 does have a communications platform. I want to say it's what is it, that RS 485 that can be taken to pretty much any modern system platform for monitoring. Yes. Yeah, they do come with communications, and AC Pro 2 and our team, for anybody that's interested, will be happy to give you all those details. I'm apologize, I don't have those in my head right now. So, any other questions?
No, that's it. But I do like the analogy about when Finley talks about putting your hands together and pressing for 5 years and then expecting it to operate. I was on a plane for way too long yesterday, and I can tell you I was stiff getting up out of my chair. So I wouldn't expect your components to sit stuck in that position for 5 years to work 100% without maintenance and proper exercise.
Yeah, no, exactly right. And once again, some equipment's more subject to failure in those situations than others. I mean, like the Pringle switch or the bolted pressure style switches shown here. These, the manufacturer says to open and close these every 6 months. So once again, it depends on the equipment. And I can tell you when somebody says, hey, I got a Pringle switch and we don't know the last time it's gotten opened, I go in with all kinds of extra tools because we know we might have to pry it open the first time, clean, lubricate, operate it a dozen times to get it working again. So it does vary from equipment, condition, criticality are important. So continuing that discussion on system modernization, a lot of folks, whether we kind of talked about breakers and older style trip units were being replaced with newer style trip units. Same thing on medium voltage systems or systems that have, like they say, your older mechanical relays. You can see the older mechanical relays on this line right here. And once again, these things have operated tirelessly. They're great if you maintain, and once again, electromechanical relays are recommended to be maintained every year because once again, it's electromechanical device. So it's subject to, those types of failures. But like I say, replacing those with, microprocessor-based relays, and in this case, the customer used multi-lin relays, but you can use an SCL relay, a Siemens relay. There's many manufacturers of microprocessor relays out there. But once again, we get a lot of benefits from these types of relays, right? Not only do we get communications and oscillographic records and things like that, where we can analyze faults, we also get, once again, greater selectivity, once again, to manage our safety, to improve minimize the arc flash hazards, et cetera. And then once again, we're also seeing where we can actually have a couple of different things that also allow us to minimize arc flash hazards, taking advantage of system modernization. And that is, using what are called maintenance bypass switches, right? So in this case, the maintenance switch is shown enabled. And what that does is it basically, it's a set of contacts that tells the trip unit use an alternate set of settings. So basically it lowers settings, in particular the instantaneous, which you might have set it 7 or 8 times. It will lower it down to 1.5 or 2 or whatever it's set for. And by doing that, if somebody's working downstream of this breaker, doing switching, taking the voltage reading, if something were to go wrong, the arc flash hazard will be greatly reduced in that situation using the maintenance mode, right? But I also want to stress that these are great, but you got to make sure that when you're done, you put it back into the normal mode, right? So that the settings go back to their higher settings. Once again, in a normal system operation, we're trying to balance safety and reliability. In a maintenance mode, we're preferring safety. So once again, we got to make sure that after we're done with what we wanted, what's preferring the safety, that we flip it back so we achieve that kind of balance system where it's balanced between safety and reliability. So remember to put your maintenance mode switches back in normal mode when you're done with whatever might be being maintenance. And then once again, a lot of manufacturers coming out with some great products to reduce arc flash and to basically almost eliminate arc flash hazards altogether. They can't technically say that on your label, right? But if we install like a relay like pictured here, and it's got these fiber loops and point sensors, and those are installed along the buswork or in the cubicles of the breakers, then basically it's taking into account 2 factors. It's looking for fault current and a flash of light, right? Which is what, is a precursor to the arc flash, right? You'll see that flash of light. And so these relays, if they get those 2 inputs, a overcurrent event and a light event, they trip, and they trip very, very fast in those situations. So what might normally be without the photo sensors, without the fiber loops, what might be, I'm stumbling for a number, but what might be a little bit longer fault waiting for the overcurrent to clear it, it says, no, it's not only an overcurrent, it's actually an arc flash event. Let's clear even faster. So once again, these can clear so fast that basically before the arc event really even gets going, the system removes the power and the arc extinguishes, right? So basically, I don't want to ever say that you'll reduce your arc flash hazard to zero, but utilizing this technology does greatly reduce the arc flash hazard to those that are working in it, and it also protects the equipment. So, on that note, Justin, let's open it back up, and hopefully there's some other questions that we can talk about. But as I wrap up, where do your issues hide, right? We've talked about a lot of different, things that we see on a regular basis. And, obviously it starts with, did you have good acceptance testing? Do you have confidence in your system when you first turned it on? What have you been doing to maintain that system? And what things are you doing to maybe take care of some arc flash mitigation, right? What technology out there could you implement to, once again, either reduce the arc flash hazard or get your technicians away from it? And once again, remote racking systems, remote switching systems are out there and available. And then I guess finally, hey, what's the redundancy? And I got a picture of some spare breakers sitting here on the floor. And once again, I recognize that that's an AC Pro. I say it's an AC Pro, I could be wrong, but it's a more modern trip unit. But once again, they're sitting here on the floor with a trash bag kind of half over them. Are these ready to go into service? Are you sure? So once again, what kind of challenges or issues do you have, and how is that going to affect the safety and the reliability of your system? So, any other questions in the chat?
Yeah, there's a couple coming in here. I have a comment that says, interesting example with ground fault protection set at minimum, pickup and delay. People may think this could be an issue with only larger fuses. We had a virtual carbon event, 1600 amp breaker with 100 amp ground pickup and 0.1 second delay that did not coordinate with a fault downstream of a 35 amp fuse. Thanks for the presentation.
Yeah, on that one, I mean, it is, I get a call probably, 2 or 3 times a year, maybe, asking how come the electrician that was wiring in the light switch and his screwdriver got, for whatever reason, he was working it hot, right? You shouldn't do that, but he was, and his screwdriver got between the hot lead and the metal case of the box. And instead of the 20 amp breaker tripping, or instead of the 400 amp breaker that feeds that tripping, it goes all the way back to the 4,000 amp main and shuts down the entire facility. And once again, that is almost always because of the ground fault setting not coordinating with the devices downstream.
I have another question. What are your thoughts on arc resistant gear?
So arc resistant gear is fantastic, and for those of you guys that are not familiar with the arc flash gear or arc resistant gear, it's essentially built like a tank, right? It has thicker steel, bolted covers, and also incorporates channels and I'm not going to pronounce this right, flumes, chimneys, that basically direct any arc that were to occur away from where the operator would stand. So if I'm standing in front of a piece of arc resistant gear, I'm going to see big, heavy bolted covers. And if there were to be a fault, there is a channel way to direct that arc blast away from me and out the back of the gear in some fashion. So it basically protects the worker more than anything else. There are other technologies out there, and it's amazing some of the technology. There's arc quenching gear now. So once again, a similar thing that the system recognizes when there's an arc event, and it throws a bolted fault onto the system to basically operate the protected devices even faster. So once again, quenching that arc or eliminating it really before it can ever get started is another example of arc rated, arc resistant. I shouldn't call that arc resistant. That's arc quenching type gear. So yeah, and I guess I should go on to add that arc resistant gear is very, obviously much more expensive than your standard stuff because of the way it's constructed.
One thing that's coming to mind for me is we didn't talk a whole lot in this about lubrications. Obviously, that's a pretty critical thing too for your general maintenance. And I guess you experience to deal with that. We deal with that in our service shops, but also in the field a lot too, right?
Yeah, I mean, lubrication in the field is one of those challenges. We all talk about it. We all recognize there's challenges. The one thing I guess I would warn our viewers about is the use of spray lubricants, like WD-40 is an easy example that everybody recognizes, but there's other type of penetrating spray lubricants. And if you have a breaker that's not operating properly because of lubrication, that is one of those Band-Aid situations I mentioned. That's fixing the symptom. It'll get your breaker working again. It'll get it operating properly, yes. But in in a month, 6 months, a year, you're going to be right back where you were with this breaker, because that's going to evaporate. It's going to go away. And you're also washing out whatever remaining grease was in there when the breaker was first built. So we got to be really careful. There are things we can lubricate in a maintenance situation in the field, but there's a lot of things like bearings and other rollers that are not easily lubricated. So once again, the big warning is if you or your maintenance personnel are using any kind of spray, know that you're putting a Band-Aid on a problem, and you probably should take that breaker out of service, get it remanufactured with new bearings, new grease, have it torn down and put back together by a qualified, and I would always recommend a Pearl accredited company.
Paul says we typically high current test the 480 volt power center breakers every scheduled maintenance outage. It's at a power plant. The breakers are also fluffed and buffed each outage, tested at 4 points along the curve, and if not within spec, they call in a design engineer. Also, we utilize zone interlocking on the 480 volt power centers to reduce arc flash incident energy, and this was before the fiber optic systems were readily available.
Absolutely.
So, sounds like great practice.
Yeah, other great practices right there. Once again, for those that aren't familiar with zone interlocking, the breakers are communicating with each other. So if the main breaker sees a fault and none of the feeder breakers see a fault, then it's going to trip at a faster time delay. And basically, once again, in an attempt to minimize any kind of arc flash hazard. You might also see this as a bus differential system on some of your larger power systems, like medium voltage. You'll see bus differentials doing that same type of task.
Mose, that's our questions and comments right now. I don't have many more.
Well, we'll start wrapping up. I mean, obviously, guys, if you have any other questions, please dump them in the chat. But some of the key takeaways, hazard risk assessment should take into account the following. We got to evaluate the condition of the equipment, and I've talked a good bit about that. We got to talk about the maintenance history. If you got equipment that hasn't been maintained in more than 5 years, you probably need to escalate that, right? Because you're kind of you shouldn't say kind of getting in, you're getting into that. Is it going to operate? Is it not going to operate? Danger zone. You definitely want to review your labels. You get to routinely walk plants, and sometimes they make no sense, right? The arc flash level is higher in one location and lower in another when I would expect them to be the same. Those types of things, and just to kind of review those. And then once again, every 5 years, reviewing your system. And then anytime you make any changes, right? If you add a system line, we want to make sure that you get a study done. Any major changes, the utility puts a new, larger transformer outside your building, that's going to necessitate a review of your arc flash study, because once again, if they put a lower impedance transformer outside your facility, your arc flash study needs to be adapted to that. And then once again, all those changes that I mentioned at the beginning of the presentation in the 1584, once again, in particular, the enclosure sizes is one I think is going to impact a lot of people. And then once again, just some key takeaways for some mitigation. Start off with some great acceptance testing. Do that routine maintenance testing. And I didn't drop this phrase in here at all. Avoid the normalization of deviation. Right? A lot of times we just say, oh, that breaker always trips a little slow, or oh, that light's always off, or we'll get to that battery system tomorrow. That's normalizing a deviancy, right? And if we continue to do that little by little by little, we are going to set up a row of dominoes that all it takes is one little thing to go wrong. And then all those things that we've been kind of ignoring or kicking the can down the road come back to bite us in the butt, right? So make sure we're doing that. And then, like I say, take advantage of modernizations, take advantage of remote racking and switching. If you can't if you got a high arc flash hazard, a category dangerous in a location in your plant, how can you operate that equipment remotely, right? Remove the worker from the hazard by taking advantage of the remote switching and remote racking that's available, not only from our companies, but from others out there on the market. And so, like I say, I got a list here of our key Oh, I forgot. I forgot to change key points of contact. So I got a slide here for our key points of contact. And like I said, myself, Mose Ramieh with CBS Field Services. You can find me on LinkedIn. Our company is also on LinkedIn. So please, if you're not following us on LinkedIn yet, do that. Do me first, and then sign up on CBS ArcSafe's page, because Justin and I are having a little follower competition. Whoever's got the most followers at the end of the year wins a steak dinner or something. And so once again, you got Justin's email address up here. And then finally, if you need pieces, parts, breakers rebuilt, you name it, we probably got it. We're trying to be the #1 needed now supplier of all things electrical. I put Joel Benson's number in or email in here. He is the VP of sales. Yeah, VP of sales for CBS. And he will direct you to the right region and individual to help you take care of your needs. And once again, you can always call me, contact myself or Justin, and we will get you to the right help that you need.